Hello everyone, this is video 5.1. We're going to be looking at fraction multiplication. So let's get started. So I want to start with remembering a basic definition that we've used of multiplication. Because we've talked about multiplication before already, and in chapter 5 we're looking at sort of extensions of multiplication. So the idea of multiplication isn't new. And so one of the definitions that we've used has been this idea that m times p, so m times n equals p. And so we can think of m groups, and then this is how many units there are per group, and this gives us the total number of units. So for example, we could do 3 times 5, and so we've got three groups of 5. So 1, 2, 3, 4, 5, like this. 1, 2, 3, 4, 5, like this. That's terrible looking. I got to fix that. That's better. And then 1, 2, 3, 4, 5, like that. So we got our three groups of 5, and we talked about in chapter 4, we can collapse these into a rectangle, and then we can see the 3 times 5 and the 5 times 3. But we started off by talking about this in this ordered way, that we've got one factor is the number of groups, and the other factor is the size per group. And then if we put all that together, then it gets the total number of units. So when we're going to start talking about fraction multiplication, we can use this definition to start off with. So once we get a little bit further into it, we'll need to extend this definition and this model a little bit, but this is a good starting point. So we can look at problems like a fraction times a whole number. So say we have 6 times 2/3. So we could take this as 6 groups where each group is 2/3. So we could draw this out. So we'll need 6 groups of 2/3. And so we could draw the 6 groups and color those all in. But what I'm going to do instead is I'm going to write, this is my group 1 right here. And this is my 2/3 of a whole, right? Now, we may need to sort of remind our students that each of these is one whole. So we don't want them to think that these 4 pieces collectively make a whole, because then each of these pieces would be a quarter, and then each of these smaller pieces inside would be a 12th. That's not what we're doing, right? So this whole collection would be 4, and so each one of these smaller rectangles would be a whole, right? So there's one group. I'm going to take another group. So there's a third and there's a third. I'm going to take another 2/3. 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 And so there's my 6 groups of 2/3. And I see that this makes 4. I could also do this on a number line. So mark off 1, 2. And so I can mark that as group number 1, 2/3. I'm going to make a big mark here to show 1. And so then group 2 would go another third and another third. So there's group number 2, which gets me to 4/3. I could mark off another 1, 2, and now that makes, this is group 3, and that makes a total of 2. And then go 1, 2. You can see where this is going from here. 1, 2, 1, 2. So this is group 4, 5, and 6. Gets me to 3 and 4. So I could use this number line model to show the same sort of idea that we did with the strip model. And then lastly, if we really wanted to do it this way, we could all go all the way back to talking about multiplication as repeated addition, and just add 6 of these together. And so we've got 2, 4, 6, 8, 10, 12. Now, we're going to have a lot of students that are going to want to make this 12 over 18, but we got to remind them that the denominator tells us the size of the piece, and when we're adding those pieces together, the size didn't change, so the denominator didn't change, so we get 12 over 3, which is 4. So here's 3 different ways of talking about this whole number times this fraction without doing any algorithm and without introducing anything new. All 3 of these things that we've looked at, this area or strip model here, this number line model here, this repeated addition here, all 3 of these are all things that we've looked at up to this point. We're not introducing anything new, and we're also not starting with the algorithm, right? So if we've built these ideas, I know I've said this a ton in this class already, but if we've built these ideas, we can go back to them, we can recall them, you know, depending on how long it's been since we've done them, we may have to remind students, hey, let's go back and look at this thing that we've done before. We're going to need this for today. It can be part of your opening activity, it can be part of your warm up, it can be part of whatever is leading into the main body of the lesson itself. But it's there. I mean, it's there to use. So we're not doing anything new yet. So now let's look at a fraction times a fraction. And this gets a little bit harder. If I wanted to do, say, 1/2 times 1/3, well, what works nice about the integer or the whole number times the fraction is I'm taking a whole number of groups. So that works out pretty well. I know what 6 groups look like. And even if I had a problem like 2/3 times 6, I know I have commutativity. So the 2/3 of a group, I'm not really sure what that looks like, but I can switch it around and make it the 6 groups of 2/3 and get it in a way that sort of makes sense. But if I'm doing a fraction times a fraction, excuse me, it's hard for me to figure out what half of a group looks like. It's hard for me to figure out what a third of a group looks like. This is going to be a little bit harder to do visually. So let's look at one way of sort of showing what this would look like. So I'm going to draw a rectangle, and I'm going to break it into 1/2 this way, and I'm going to break it into thirds this way. And that doesn't really look an awful lot like thirds. Let me fix that. That's a little bit better. Okay. Now, depending on the book, you may see this a couple different ways. So I have seen this where you shade the 1/2, and then you also shade the 1/3. Now, I've also seen it where you shade the 1/2, but you only shade the 1/3 that overlaps. You wouldn't shade this part over here. And I see both sides of why you might want to do that. If you just shade the 1/3 that overlaps, then you're taking specifically the 1/3 of the 1/2. What I don't like about that is that you don't see the 1/3 of the whole. If you shade the whole thing, then I like that you can see the 1/2, that you can see the 1/3. But what I don't like about it is that there's so much more going on in the diagram in this model. I would expect a lot of students to give 4/6 as an answer because 4 of them are shaded in. I would expect to maybe see 1/4 as an answer because there's one that's double shaded versus 4 that are shaded. There's kind of a little bit more going on in the model this way. And I know it's only one additional section that's being shaded, but the fact that there's an overlap plus some that aren't, and there's a little region that's not shaded by anything, that one additional piece is still one more moving part. So, look at the way that your curriculum is doing it. Talk with your host teacher or other teachers on your team, and see which interpretation or which representation of this model is being used. But you'll see both. And if you go on YouTube and watch videos about sort of this model for fraction times fraction, it's not going to be too difficult to find both models being shown as well. So just be aware that both of them are out there. So now we look at how many pieces there are total. And so we know that 1/2 times 1/3. Well, this whole thing is broken into sixths. And so this is my unit rectangle being broken up. And then how many are shaded by both? And so we get 1/6 for that. Now, if I wanted to extend this problem and do, say, 1/2 times 2/3, I can do that as well. The model's going to look almost identical. So here's my 1/2, here's my thirds. I can label this 1/2, 1/2, 1/3, 1/3, 1/3. And so now I can shade in my half. I'm going to cross shade my 2/3. And now I can see what I have here. And so I've got 1/2 times 2/3 equals 2/6. Now, if I want to look at how two of these pieces can partition this space in three equal sized parts, then I can see that this is the equivalent fraction to 1/3. So I can go back and look at ideas of equivalent fraction. But for right now, what I really want to focus on is this multiplication model. And so this is a really good starting point for introducing fraction time fraction multiplication without going straight to the algorithm. So now we can get to the actual algorithm. So we see that 1/2 times 1/3 was 1/6. And so what are we doing here? Well, we're taking the numerators and multiplying them together. So this is 1 times 1. And then we're taking the denominators and multiplying them together 2 times 3. There's nothing wrong, again, with getting to the algorithm because it is quicker. I mean, it is more efficient. Again, we don't want students having to draw rectangles every time they need to multiply fractions. But the algorithm needs to be supported by some sort of model, some sort of visual, some sort of understanding. So I would not start with the algorithm. I would not just do the algorithm. There needs to be something that leads up to it. And students should be able to understand why this algorithm works. And realistically, it's not that complicated of a model. If I take a problem, say 2/5 times 3/4. So without really drawing the rectangle, I know that my rectangle is going to be broken into 4 by 5, right? So this is going to be 4 and this is going to be 5 without actually drawing it in. So I know that this rectangle is going to end up broken into 20 pieces. So I can see this 5 times 4 making this 20 just by having used this rectangular array so many times in the past. And so again, building that understanding before pays dividends moving forward. And so now I know that 2 of these were shaded in, and I know that 1, 2, 3 of these were shaded in. And so I know my shaded in rectangle is going to be 2 by 3. And so that means I'm going to have 6 of them shaded in. And again, I can see what's happening here. This is my 2 times 3 equals 6, and this is my 5 times 4 equals 20. So it's not that the algorithm is bad or flawed or wrong or incorrect, but when it's sort of floating in the student mind without any sort of connection to anything visual or conceptual or structural, that's when we get some issues. So now we can go back and look at mixed numbers and improper fractions and how they relate to multiplication. And really, there's not a whole lot new here. Um, we need the same sort of ideas around fraction multiplication that we had before, and we need the understanding of how mixed numbers and improper fractions that we have from before. So not a whole lot new here. Let's look at, as an example, 1/2 times 2 3/4. And I want to look at two different ways that we can solve this problem. And so one way we're going to do it is by just converting this all to improper fractions. And so if we change this to improper fractions, we get 3 over 2 times, and so this would be 4, 8 plus 3 makes 11 fourths. Right. So now if I were to draw a rectangle for this, how would I break this up? Well, I'm still doing this first part in halves. So I still want to break this into halves, but I need 3 of them. So I got 1 half, 2 halves, 3 halves. And you might see people draw this line a little bit darker because it's going to represent this unit, this whole. And the same thing is going to happen over here for the fourths. I've got 1. Here we go. And then 2, 3, 4. So that should make 11. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yep. So we've got, these are all 1/4, and I'm not going to write this 11 times, but you get the idea. So 1, 2, 3, 4, and so I can shade this in and show that this is a whole. I got a little away from me there. Let me fix that. All right, so I'm going to shade this in and make it a whole. 1, 2, 3, 4. I can shade this in and make it a whole. And I can see here that this also makes the 1 1/2. This makes the 1, 2, and 3/4. And we're going to carry that idea over into the next model for this. But I just want to show that this is all still represents the original problem. So now I got to look at what these pieces are. And this is where this gets confusing. Because a lot of, oh my goodness, I labeled that as a third. That should be a half. A lot of students are going to look at this and say, okay, well, there's 3 by 11, so this is in 33rds. And that's not correct, because we're not saying that this entire large rectangle is a whole. And this is where this gets a little confusing. This is a 1, and this is a 1. And so by marking off this unit, we can see that there's actually 8 pieces that go to make a whole. And so there's a reason why we want to mark off the 2 halves and the 4/4, is it gives us an idea where this unit is. I can also see that this is a unit. Now it's a little bit harder to see that down here that this is a unit, because there's 1, 2, 3, 4, 5, 6, 7, 8 pieces down here. And then, we can kind of move some pieces around here as well. But we can kind of see where all these pieces lie. But each of these is going to be 1/8. And so now we're going to count together how many pieces we have. Well, we've got 33, and all these pieces are 8s, so we get 33/8, which is 4 1/8. And like we said, we can kind of color these in and show, well, here's 1, and then here's 2, and then here's 3, so we'll shade in 8 there, and then here's 4. So 1, 2, 3, 4, 5, 6, 7, 8. So we've got 4 groups of 8 with 1 left over. That makes 4 1/8. Now, you could, if you wanted, instead of drawing just the 3 halves and just the 11/4, you can extend this down and make it 2, and then add on this extra 4th and make this 1, 2, 3. And then you have this sort of negative space in here that's not being used. I can see the reasoning for wanting to do that. I'm not a big fan of that. I think you're adding in more pieces again. I just want to look at sort of like what's necessary for this problem, and develop this model this way, rather than have those extra pieces. The reason why we have those extra pieces when we did fraction by fraction was because we needed to see where the unit was. And without knowing where the unit is, it's impossible to know what the denominator is, because we don't know how many pieces go to make the unit. Here, because the model is bigger than the unit, we don't need to extend this out. We've got everything we need. Once we have this first unit rectangle, we're good. We're home free. Let's look at the other way of doing this problem, which is a little bit more complex. But I could do this as 1.5, and then do this as 2 3/4. So I'm going to keep it as mixed numbers and not do any improper fractions. And really, I'm doing like 2-digit multiplication that we looked at before and using my area model. So this is going to be 1 times 2 is 2. 1 times 3/4 is 3/4. 2 times a half makes a 1. And then a half times a 3/4, well, we've already done fraction times fraction. So we're just going to bring this back from what we've done already. So this makes 3/8. And so when I add all this together, well, this is 3. This makes 6/8. So this is 3 plus 9/8, which is 4 plus an eighth. Or as a mixed number, we just write that as 4 and 1/8. This is probably a good time to remind students, that a mixed number shows addition, not multiplication, is a little confusing because if they've seen something like 2x, then they know that things written next to each other represent multiplication. But a mixed number behaves differently. That's two numbers that are written next to each other, but they're not multiplication. A mixed number is specifically addition. So if students have seen this sort of thing, if they're aware that this sort of thing exists, just remind them that 4 and 1/8 as a mixed number is not the same thing as 4 times 1/8 written as a product. Both these models work. You can do the one that kind of makes the most sense for you. I would probably lean toward the left one to start off with, and then maybe build to the right one as another model or as maybe like an enrichment model. I think the first one's a little bit more concrete, makes a little bit more sense. But if you know the students are really struggling with converting mixed numbers to improper fractions, maybe you just leave that one alone and go with the second one. So you'll have a better idea what your students are capable of and what they understand once you get some time working with them. Okay, so for your checkpoint problem, I just want you to look at 3/4 times 5/7. Can you model and solve that problem? I'm going to try to do mostly problems that don't have equivalent fractions where there's not reduction or simplification that you need to do, because I don't want to conflate that with what we're doing. So most of the problems that you'll see, they won't reduce. Later on, we'll see some, we'll get into some problems where they do once we're ready to start combining those ideas together. If you want to make this a little bit more complex, you can make these the mixed numbers 1 and 3/4 times 1 and 5/7, just so you get some practice using mixed numbers as well. You can put integer values in front of those. As always, if you have any questions about this problem or anything else from this section, by all means, please ask. All right, thank you.